Good morning, everybody. I know the screen looks like an absolute mess, and it is. I mean, there's no way around it. But in order to save ourselves from having to reinvent all of circuit theory and having to deal with differential equations and time dependence in our circuits, remember, we're doing this convention. I like to call it cheating, okay? Because it feels a little bit like we're cheating. We're cheating our way through AC circuits by treating them like DC circuits. And the way we do it is we turn inductors and capacitors into resistors. So in the end, it's like we just have to add 3 resistors together, which is something that we know how to do. So, but it comes with caveats and consequences, like this impedance thing right here, this big capital Z, right? That gets re-derived for every AC circuit. Like if this were a parallel RLC circuit, we'd have to re-derive this relationship right here. Weird things happen with like power factors. But the good news is in the end, we have all the equations we need to be able to do a series RLC circuit. And so I just want to do some examples of that today. And then we'll transition into why AC circuits. Like why is it so important that we do AC? And then we'll finish up chapter whatever we're on, 31. And maybe I don't know if I'll start 32 today or not. We'll find out. You'll notice that I wrote something across the top called Eli the Iceman. That is a mnemonic that you're going to hear in the context of circuits. Okay, and so I do want to explain a little bit about what it means, because conceptually, I mean, it'll crop up if you ever have to do any kind of circuit conversation. Okay, what Eli the Iceman is trying to remind us of is the order of like who's ahead and who's behind. Remember, we're hiding this time dependence. But last time when we were together, I showed that simulation with the phasors. And we saw that the inductor was ahead of the resistor, was ahead of the capacitor, that kind of thing. This Eli the Iceman is trying to help us remember that. So how does that work? The EMF, the E, right, in Eli, okay? The voltage in the inductor is ahead of the current in the circuit, right? So if I had like the phasor picture I get in my head, right, is where you have the voltage through the resistor, and then you have the voltage through the inductor, and then you have the voltage through the capacitor, okay? And they're all at 90 degrees to each other, right? In a series RLC circuit. As this whole phasor representation rotates around, right? Doesn't matter where it is, the 90-degree angles stay. And the voltage through the inductor is ahead by 90 degrees, and the capacitor is behind by 90 degrees. So Eli the Iceman, the voltage in the inductor is ahead of the current in the circuit. Where would the current in the circuit be? It's right here. We're tracking it through the voltage in the resistor. The resistor being the only kind of real thing in the circuit, right? It basically follows what the power supply is doing. So Eli, with L being in front, right, of the current in the circuit, means the inductor's ahead. And then ice over here, right? Do you notice how the ice, the E, is behind? It's got a conductor, so the current comes first, and then the voltage for the capacitor, right? That's what Eli the Iceman. So you'll see electrical engineering students kind of wandering around going, Eli the Iceman, right? Like trying to remember that in a series RLC circuit, the inductor's ahead, the capacitor's behind. The resistor or the current in the circuit is in the middle. Okay, so that you'll hear that. You'll see that on various websites and various videos and things like that. So I didn't want you to be totally confused when you ran into that. Okay, with this toolbox in place, we should now be able to handle various problems, okay, in a series RLC circuit. So I'm gonna throw 3 examples at you, And I want to show you like how you can use this toolbox for various circuits. It's not just always RLC. It's a series RLC, but we can take out resistors, capacitors, inductors, and all of our toolbox still works, right? If something's missing, if you have a circuit that maybe is only RC or RL or something like that, or just LC, just set the effective resistance of that element to 0. So in this problem, right, what have we got? It says we have a resistor and a capacitor, right? So what I like to do is I like to draw a picture. So I start with the power supply, right? And then it tells me I've got a resistor and I've got a capacitor. It doesn't matter kind of where I put those in the circuit because it's series. So I've got my resistor, I've got my capacitor, right? What's missing? The inductor. So what are we going to set the inductive reactance to be? If it's not there, it's 0, okay? All right. They want us to find current, right? What is the RMS current in this circuit? If this were a standard DC circuit, like the one you did yesterday, okay, how would you find the current coming out of the battery? Like, how would we calculate it? Not Ohm's law yet. What's the first thing you have to do? Because there's 2 resistors in this circuit. We combine them, right, into their total effective resistance, equivalent resistance. We then use Ohm's law to find the current that's coming out of the battery, right? Well, here we don't have a battery, we've got a generator. And we don't have resistors, we have capacitors also. But again, remember, the cheat is that we are going to treat this capacitor as a resistor. And when we go to find our equivalent resistance, we're going to use the impedance. So first thing I need to do is figure out what my reactive capacitance is. And do you have any notes? What's the reactive capacitance equation? 1 over omega c, right? Okay. So now we need to find omega. Oh dear. What did they give me up here? 100 hertz. Is hertz omega? No. Omega is equal to 2 pi f, isn't it? So I take 2 times pi, and then I multiply by 100, and I get 200 pi. I don't have my work for these. I don't know what I did with these notes. So get your calculators out. You guys have to do some work today. $628 radians per second. Okay. Whew. So I now need to calculate that. I need to go 1 over 628 times my capacitance. Okay, they gave me the capacitance. I'm going to put 0.25 times 10 to the minus what? 6. Micro means 10 to the minus 6. And this will get me my capacitive reactance. Ratio. Has anybody got it yet? You're going to win because I don't use calculators all that much. 6 multiply 1 over. I got 6,370. Is that what you said? 6,370? 6,370 watts. What are the units here? Don't think too hard. We just turned it into a resistor. Ohms. Okay. All right. Now that we have that, we can go ahead and calculate our impedance. Remember, impedance is the equivalent resistance. We don't do just add them together. This is an AC circuit. So we can't just add them like we would with DC. We do have to go through the impedance. So that's R squared plus XL minus XC quantity squared. The XL is 0, so that's kind of nice. So the resistor, 10,000 squared plus 6,370 squared. What happened to the minus sign? It's negative sign. It's going to get squared, so who cares? I got 10,019. Yeah? 10,019 ohms. Now that we have that, we can use what? Because you're probably smarter. Did anybody else get that? What is it? Thank you. My calculator lied to me. I'm glad I have built-in error correction. That's awesome. Okay, so to solve for the current in this circuit using Ohm's law, it's going to be voltage divided by resistance, but instead of the equivalent resistance, it's going to be the impedance of this circuit. So what have I got? My 20 volts all over 11,856. Yeah. I got 1.7 milliamps. Yeah? 0.001686996. Close enough for me. Okay, let's step back, right? To do an AC series AC circuit, we did the DC methods in the sense that we wanted to collapse the circuit down into its simplest circuit, like a single equivalent resistance. Instead of using like series and parallel resistor rules, our equivalent resistance is the impedance. But to calculate the impedance, I need to know what the reactance is for the things in my circuit. So I calculate those, I calculate my impedance. Once I got my impedance, I use Ohm's law, and I'm done, okay? So a lot of this is very plug and chug. A lot of it you're sitting there questioning your life choices. Why do I have to learn this stuff? That's coming, okay? But I want you to see, right, that our toolbox, if we can put the pieces together in the right order, we got it. I always start with just finding reactances. I know I'm going to turn everything into a resistor, so just turn everything into a resistor. And then I calculate my impedance. They might not even be asking for it, but if I'm going to have to calculate a current or anything else, I'm probably going to have to use the impedance, right? And so on and so forth. So I just kind of use my toolbox and put all the pieces together as I go. Okay, new problem, okay? We start reading, not even thinking about what they're asking. We got a resistor. Yes, okay, what's our picture going to look like? It's going to be a generator attached to a resistor so far. Okay, we got that, right? So we have the resistor. What else have we got? We've got a voltage and a frequency and, an inductor, right? So it's going to be resistor and an inductor. Be careful, Mr. Balogh. Try to draw it cleanly. Okay, so looks like something like that, right? What do you want to go for first? Turn the inductor into a resistor so that we know what we're doing. Okay, I like it. It's omega times L, right? I know this omega is 377. How do I know this omega is 377 without even looking? It's at 60 hertz. The United States uses 60 hertz, right? So whenever you're using mains power, the stuff that comes out of the wall, the 120 volts, it's in the United States at 60 hertz. And so I've used that so often in research and calculations and things like that, that I stopped having to do 2 pi times F, right? omega is equal to 2 pi times f, and 2 times pi times 60 is 377 radians per second. So that's why I knew that one. All right, 10 to the third, 10 to the minus third. It's a millihenry, right? Which gets me, is anybody done yet? 96.1? 96.1 watts. Ohms, right? We just turned it into a resistor. Okay, again, sort of thinking ahead, we're going to need Ohm's law to solve for the current. We're going to need the voltage divided by the impedance, which means we're going to need the impedance of the circuit. So we have a 525 ohm resistor, square that. And then we have XL minus XC, but that's just, there's no, what's XC? 0. 96.1 squared. And let's see if my calculator can lie to me again. I got 533. Yeah? Slight redemption for my calculator. May not have to change the app. I got to remind myself to not throw my phone. Right? It's the app on the phone that's at fault. It's not the phone. If it were a calculator, I'd be throwing the calculator. Just saying. All right. 533 watts? Ohms. Oh, that's not the answer. For the record, I never throw things at people. Okay? I'm a pacifist. I don't like hurting people. I will throw inanimate objects at inanimate objects. Right? But I'll never throw things at people. And I do my best to never yell at people. My kids got yelled at. But they're kids. All right. Let's see. Where was I? Calculating the current. What's my voltage? 20 volts divided by 530. What's 20 divided by 533? Or 37 milliamps, right? So, again, is the math here hard? No. Is putting the math together hard? This is no like finding the electric field of a ring, right? This is why I say this stuff is kind of easier. Yes, you can get confused. Yes, you're going to get tripped up. But I think that you have to do fewer of these to get the hang of them than, say, doing electric field or magnetic field stuff, right? Would you rather do this or Lenz's law? Right? Okay, so, right? That's kind of why when people ask me, well, this AC circuit sounds really hard. I'm like, it's really not. I mean, yeah, it can be confusing and you can still feel lost. All of that's true. You will struggle. You'll do a homework problem every hour or 4 hours, right? Like, all that's true, but like, I just feel like the mental load of this is less than a lot of the stuff that we've done in this class. I reserve the right to be wrong, and you can say, Mr. Balogh, you're so smart. I'm not. I've just been around the block a lot. Okay, what have we got in this example? We've got all three, right? You can kind of see it right there. It says RLC circuit. There's an R, there's a C, there's an L, right? So I'm just going to start right away with drawing my picture before I read anything else. R, L, no, L, C, circuit. Label them. So you can tell the difference between the inductor and the resistor. Okay, resistor we know. 9900. What did I just do there? Oh, yeah, I took the kilo out, right? And I just wrote it down as ohms because I want everything in standard units. Okay. I need X L, and XC, right? I need to convert these things into their various resistances. So 1 over, it's 60 hertz again, so I know it's 377 times 0.15 times 10 to the minus 6. You know, good notes. Can you do it? That can't be right. That is not right. Because it has to be a number way bigger than 1 because I'm dividing by a number. So it misinterpreted it. Oh, it didn't get the minus. Convert. So, am I zooming in? Yeah. So it didn't, do you see how it didn't catch the minus 6? Stupid AI. I need to fix something. I got a new iPad. Is that the one I want? So now it's not changing for you. Okay. I got a new iPad, which I'm very grateful for. The school doesn't usually buy me new things. My old iPad's battery was going bad. But when they handed me the new iPad, it had all of the CIA spy stuff on it that the school puts on there to like track, make sure I'm not playing video games on it and stuff. What they don't know is that I can get around all that stuff. It wouldn't let me do the Vulkan mind meld that Apple devices you can do. When you set up a new device, you can just like put the two devices next to each other and just copies itself over, and you've got like a clone. I couldn't do that because they had locked out that functionality, and I wasn't going to spend the time to fix it. So I'm still working out some of the bugs in my new iPad, but we'll get there. We'll get there. Okay. So why did it? Okay, darn it. I want to fix this. Sorry. What did it not like about my handwriting? Now it's not detecting it as a thing at all. The answer I want is how do I get this thing to be smart? And apparently it's, okay, what is it? Great, thank you, Rose. Okay, so 17, this is the C, 17,683. Okay, how do we do the same thing for finding X sub L, right? Well, X sub L is going to be omega times L, which is 377 times 25 times 10 to the minus 3. 9.4? Yeah, I think that sounds about right. I remember my calculations correctly. Which, okay, brings up something interesting. Let's just stop right here before we go on with the rest of the problem. How much is this inductor influencing this circuit, do you think? Not much. And what leads you to that conclusion? The effective resistance of this inductor is so low compared to the other things in the circuit that it's really not doing anything. And in fact, it seems like the capacitor is in charge here, doesn't it? It's the thing that's going to be like really influencing what's going on here. So you can pull some decent like conceptual information even out of this cheat. I mean this convention that we'd be using. All right. I haven't even figured out what they want. Find, oh, this is interesting. Find the voltage across each element. Well, the resistor is an element, the inductor is an element, and the capacitor is an element. So this is going a little bit deeper. They don't want the whole enchilada. They don't want to know the current through all of these, which we can find. And the current through one of them is going to be the current through all of them, right? Okay, we'll find that in a second because we're going to need it. They want the voltage through every single one, right? This would be kind of like we're in the lab, we're measuring the voltage across each element, and we want to verify our measurements with calculations, right? So to do that, I want to find the effective resistance of the circuit, divide the total voltage by that effective resistance to get the total current coming out of the generator. And then once I know that current, I know that's the current in all of them, and I know their resistances, so I can find the individual voltages using Ohm's law. That's sort of my process for circuits, DC or AC, it doesn't matter. That's what I'm going to do. What matters are the details, and one of the details that we need is the impedance, right? So let's see. That's going to be R squared, 9,900 squared, plus XL, 9.4, minus XC, 17,683. If anybody's doing it in this calculator, don't bother with the 9.4. Why doesn't it recognize that as a calculation to do? It's because my handwriting is so bad, isn't it? Oh. I have to learn to write clearer, and this thing needs to learn how to read my bad handwriting. Okay. Someday it'll just do it for me. Did anybody have a number yet? 20,000? Okay, that's fine. Ohms. And then, okay. Okay. So to find the RMS current, I'm going to take the voltage and divide, that's just Ohm's law. My voltage, 115. So this is just standard wall AC. Divided by 20,257. So whatever that number is. Thank you to all of my calculators. You got 5677. So this is 0.0056 whatever that is, amps. All right. So now I found the current in the circuit. Since it's series, I now know the current through all the elements. I know the current through the resistor. I know the current through the inductor. I know the current through the capacitor. I can now find the voltage through every single one. And that voltage, the voltage through the resistor, let's say, okay, is going to be the current in the circuit times what? The resistance of the resistor. It doesn't have to be the whole impedance because they just want the voltage through the resistor. So I take my 0.005677 and I multiply it by 9,900. And I got 56.2. 56.2 watts. Volts. Where's my drop? There you go. Volts. All right. Okay, so we down that. Voltage through the inductor. It's going to be the current in the circuit times what? The resistance of the inductor. Always funny to think of it that way, but that's what it is. 0.005677 times 99.4 is a small number. 0.05. 0.05 volts. And then finally, the voltage through the capacitor. Current times the resistance of the capacitor, 0.005677 times 17,683 100.4. There we go. You now know all the voltages through each of the elements in that circuit. Let's check our answer. See if it makes any kind of sense. So what happens if we add all of those voltages together? We get 156 point something, right? Does anybody see a problem with this? That's higher than the 115 volts that we started with. So we've either done something very wrong or we have broken conservation of energy, which I suppose could be defined as very wrong also. But actually we're right. It's an AC circuit. These are the RMS values for the voltages. And what does RMS mean? I know it means root mean squared. What does it mean? It's like an average, right? It strips out the feature of time. Do all of these hit their maximum voltages at the same time? No. Eli the Iceman, right? The inductor is going to have its maximum voltage, and simultaneously the resistor and the capacitor are going to be doing something else. They won't be at max. So when we strip out all of that time information, we start talking about RMS, which is averages, we have to remember that, yes, these are average values for the voltages through these things, but they're not the instantaneous value for the voltage through these things. To find that, we'd have to go back to the beginning, get our time-dependent equations for the current and the voltage, and solve for it. It's a mess, but just realize that you can't just add RMS voltages together and add them up to 115. You're not going to get the correct answer, okay? Is it true that the voltage in the circuit never exceeds 115 volts? Yes. Because when the inductor is at max, the capacitor, being 180 degrees different from it, is at min, right? Okay? And the resistor's off doing something else. So at any one given point, we conserve energy. We can't have a higher value than 115 volts in the circuit. It's just that on average, these will be the values that they have. Kirk, did you have a question? It's not a coincidence at all. Yeah, because RMS. We're doing statistics, and so we have the statistical correction that we can pick. So if a problem asks you to find the voltage through an individual inductor, right, you find the current of the whole setup, and then you just use Ohm's law focused on that inductor. And as far as checking your answer goes, I wouldn't. I just calculate it, make sure your calculator's not lying to you. And that's about all you got, because if you try to use reason to correct something that's based on statistics, you're going to go crazy. Okay, this is why we are talking about AC circuits. One of the many reasons. So what I need to do in the next 20 minutes or so is really kind of convince you that AC is worth it. That this cheat or this convention that is used in all of electrical engineering everywhere is worth the price that we pay, and that it's worth generating AC directly, even though we need DC in all of our devices. So the story begins, I've told you the story partially already. We began this entire discussion of AC circuits on the idea that Faraday's law of electromagnetic induction, when we generate electricity, It naturally comes out as alternating current. The changing magnetic flux causes that sine-cosine fluctuation in the voltage and hence the current. So we naturally generate it AC. But is there more to the story? And of course the answer is yes. What's a transformer? Yes, they are more than meets the eye. Okay, right? I use the modern Hollywood depiction of this, even though it wasn't any good. It was okay. The first half was okay. The cartoon, of course, was much better. And I cried. Spoiler: I cried when Optimus Prime died. That was a formative moment in my childhood. Anyway, no, not that transformer. This transformer. Okay, you've probably seen them hanging on utility poles, right? Those boxes. Sometimes you see them on the ground in green boxes. Okay, that say high voltage on them. But they also appear in these little tiny boxes that we use to plug in stuff, right? So in this brick, there is a transformer. Okay. If you've got a laptop brick or a charging thing for your computer, your phone, a monitor, whatever, right? A lot of times the transformers, like in a monitor, will be actually inside the monitor, okay? Your computer has the power supply inside that's got a transformer in it. A transformer's job is to transform voltage for current, and it only works if you use AC. I'll explain that. But let me be clear. These bricks also do something else. The power pole one does not do this, but your charging bricks also rectify your current. Rectifying a current means taking it from AC and turning it into DC. Okay? I really can't teach you how rectifiers work because it requires quantum mechanics. Okay? There's an element in a circuit called a diode. And what a diode, this is a very simple version, a diode lets current only flow one way. Think of it as a one-way wire, right? And as soon as current tries to flow the backwards direction from the way the diode's pointing, it stops it, okay? In order to understand how a diode works, you need quantum mechanics, okay? So you'll learn more about that in Physics 4C. But a rectifier takes a back and forth current in a wire and basically says, okay, you can go that way, but then it has to stop when it reverses, and then it can go that way, and then it has to stop that way, and then it has to, right? And so what you get is something that almost looks DC, right? It's like there's like a little, like it stops, and then it goes again, and then stops, and then it goes again. But as long as it's going fast enough, it's effectively DC as far as the rest of the circuit is concerned, okay? So a rectifier changes AC to DC. A transformer trades voltage for current. Does anybody know, off the top of their head, the standard voltage for USB? 5 volts, okay? Why is that important? It's standardized for everything. So when my phone plugs in its USB-C port, okay? When my iPad with its USB-C, with any device that's on USB-A, okay? USB-A is the flat standard. I've been trying to get rid of them in my life. Trying to convert everything to USB-C. What's the advantage of C over A? Faster. That's none of, no. It doesn't matter which way you plug it in. How many of you have sat there hunting behind the computer or whatever, you can't see the plug, like you know it's there, but you have to invert your USB plug to get it to plug in? Right? 3 times is like the minimum average amount of times it takes for you to get it plugged in. USB-C doesn't care, right? It's agnostic as far as which way it gets plugged in. Love that feature. Of course, the governing body that's supposed to set the standard then went and ruined it. Because you have USB-C standard. You have USB-C low power. You have USB-C high power. You have USB-C Thunderbolt. Who knows what that means? Because there's like 17 different versions of that. And like, is your USB-C cable okay for running, I don't know, a video signal over? Well, there's no way to tell because they don't label it. And if they do label it, the standard doesn't make any sense. Why can't they just call it USB-C video? No, they're USB-C 16 point, blah, 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 right? Oh, the standards around USB-C hurt my brain. However, all of these devices expect 5 volts. What's the voltage that comes out of the wall? 115 to 110 to 120, right? We usually say 115 average. Okay, but 120 volts max, RMS max. And so the brick is responsible for taking that from 115 volts down to 5 volts and also rectifying it into DC. Why would you want to do that? The answer is, spoiler, it's much more efficient to transmit electricity at high voltage, but that kind of electricity isn't terribly useful when you actually want to do electrical work. Let me explain. A transformer consists of a core, okay? In this case, this isn't how you actually build them, but sort of a schematic idea here. You have a primary winding, a coil that gets wound around an iron core, and then a secondary winding. The primary has some sort of input, alternating current input, okay? Goes into the primary, and then the secondary is your output. It powers whatever device is connected to it. These two coils are connected only magnetically. And why are they connected magnetically? They're wound around the same iron core. Iron is a ferromagnetic material, meaning it responds to magnetic fields, it gets happy. If they are wound around the same iron core, what can you tell me about the magnetic flux through these coils? It's the same. Whatever fluxes you have in the primary is the flux that you will have in the secondary. Quite often, in real transformers, these two coils are not separated in space like we have in this drawing. They're usually wound on top of each other, in and amongst each other. If we change the number of turns in the primary and secondary, we can pull off some pretty neat stuff. So what are we talking about? We are talking about my favorite, Faraday's law of electromagnetic induction. Okay, so in the primary, which I'm going to indicate by a number 1, okay, I have a certain number of turns and a magnetic flux. In the secondary, which I'll call number 2, right, I have a number of turns and a change in magnetic flux. And as I just explained, the change in magnetic flux is the same because they share the same common core winding. The number of turns is different, but they're overlapping each other, and so they're going to experience the same flux. The flux through one coil is going to be the same flux through the other. So if we solve both of these for the flux, B, phi dt equals 2 over n2. Okay, if we solve those both for the flux, what can we now do? Set them equal to each other. And let's say I want to solve for the voltage in the secondary. Okay, I can manipulate this. Solve for it. Did I do my algebra right? I think I did. Yeah, all right. So this ratio of turns, right? Primary or secondary to primary, right? What happens if the number of turns in the secondary is bigger than the number of turns in the primary? What is N2 over N1 going to be? It's going to be big, right? This is going to be a number that's bigger than 1, right? And so whatever number it is, let's say N2 is 10 times bigger than N1, right? We would have a factor of 10 there, wouldn't we? And so what does that mean about the voltage in the secondary? It's bigger. It's 10 times bigger than the voltage in the primary, right? This is referred to as a step-up transformer. What did we step up? What got bigger? The voltage. The voltage in the secondary is bigger than the voltage in the primary, otherwise known as a step-up transformer. But if the number of windings is less in the secondary than it is in the primary, what is your ratio going to be? It's going to be a number smaller than 1, right? And if we had 10 times fewer windings, right, we would have like a 1/10 here, right? And so our voltage would go down by a factor of 10. You want to take a guess as to what we call this one? Step down. But it's important to realize what is being stepped up and what is being stepped down. It's voltage, right? So we have a way in a transformer, which is the physical manifestation of Faraday's law of electromagnetic induction, to change voltage on the fly. If I need more voltage, I just put more windings in my secondary than I have in my primary. And I can tune it to whatever voltage I want, right? If I know I need 5 volts out and I'm doing 115 volts in, that's going to be a very specific ratio of windings that I need to make that happen. But you can't get something for nothing. There has to be a trade-off here, right? If we're getting more voltage out, what pays the price? Current. Okay? So current does the opposite. If your voltage is being stepped up, your current is being stepped down. And vice versa. If you have a step-down transformer, your current goes up. So in our power bricks for our phones and devices for USB, when we want 5 volts, we're going from 115 to 5, right? What kind of transformer is that? That's a step-down transformer. What went up? Current, okay? So we're able to get higher currents out of that situation, do things like fast charging and all that kind of stuff. There is no one standard for current in the USB specifications. Don't misunderstand me. There are certain like USB power delivery and stuff like that where they set like maximums. They say like don't go over 40 for this kind of wire. Like the actual physical plug itself is only rated for so many amps of current that can flow through it, right? But it doesn't have to always be that number. The voltage will stay because it is always 5 volts, right? But the current will change depending on like what the device is trying to draw, whatever's going, like if you're compiling something, playing a video game, things that are using a lot of computational resources, right, will pull a lot more current, but the voltage will stay the same, right? So the amount of power that we have stays constant, right? It doesn't matter if we're delivering 40 watts of power at 115 volts. That 40 watts of power will be, if the brick calls for it, 40 watts of power will go through. It's just it's going to do it at a different voltage and current configuration, depending on batteries like currents to charge with, but not necessarily alternating currents. We'll get to DC here in just a little bit. All right, so transformers allow us to step up and step down, okay? So this is not hard. In fact, this is easier than AC circuits, okay? So the input is 120. So what does that mean the voltage in the primary is? It's 120 volts, right? Okay. Now the current in the primary is 5 amps, right? I guess I should probably come over here. Did I work out? Yeah. I told you that like energy is conserved, right? The power has to be the same on both sides. And if we go back to power, power is current times voltage. And so this tells us, right, current in the secondary is going to be equal to the ratio of V1 to V2 times the current, right? So there's your like equation for currents, right? And it turns out to be the opposite of what's going on in the capacitors, or the for the voltage. All right, so what do we got here? We got 120 volts from my primary at 5 amps, right? And they tell me that the number of turns in my primary is 800, and the number of turns in my secondary is 200, okay? Output voltage and current. Step up or step down transformer? Step down. We're going from 800 turns to 200 turns. It's going to be step down, right? We reduce the number of turns. Let's see what the math tells us, right? N2 is 200, N1 is 800, and the voltage was 120. So that's is 200 over 800 1/4? Times 120, which last time I checked was 30. Did I get that right? 30 volts. Okay. So there's the output voltage. And then the output current. If the voltage went down by a factor of 4, what did the current do? Went up by a factor of 4. So there we have it. What's the greatest difficulty in that problem? Basically, right? Not getting your numbers flip-flopped, right? Between secondary and primary. Okay, so what's going on here? Why AC for transmission? Why DC for devices? So on and so forth. And what does this have to do with Nikola Tesla and one of the greatest jerks that ever lived, Thomas Edison? When you generate electrical power, again, you naturally generate at AC, right? We're turning loops in the presence of magnetic fields, and we can get this electrical output. Devices like light bulbs, they don't care what direction the current is flowing. You can do DC or AC. The filament in a light bulb, so I'm thinking like in one of those old-fashioned incandescent light bulbs that literally just heated up the filament. The filament's going to heat whether the current's going that way or that way. It doesn't matter, right? And if at 60 hertz or 120 times a second, this current is flipping back and forth, are you going to see the light bulb's filament flashing? Does anybody know what the frame rate of our eyeballs is? It's 20, what is it? 27.4, 28 point, like, movies are displayed at about, well, they used to be like 24.77 or something like, but now it's 30 frames per second, okay? At about 30 frames per second, our eyeball-brain interface loses the ability to see distinct frames of a movie, okay? Now, can we detect the difference between, say, a 30 hertz display and a 60 hertz display and a 120 hertz display? Yes, but that's more of a feature of like being trained to see the differences and the feel of the entire user interface as it does stuff, right? That's not the actual rate at which our brain eyes like can distinguish frames from each other. I can tell the difference when my video game is playing at 30 or 60 or 120. Like the video game just feels smoother to me, right? But in terms of like, does it still look like video? Does it, right? I'm not seeing like individual pictures of the cartoon frame, right? Past 30, I can't, my brain, eyes, we can't see the difference, right? So if something is going at 120 hertz, we're not going to see the individual flashes, right? Now, these LED light bulbs in this room, wish I could demonstrate this for you. They are flashing right now. They're flashing at a slightly different frequency. But if we were to record with, say, video, especially like slow-mo footage and all that kind of stuff, we would see the flash of these lights, the LEDs going off at different times because they're moving at different frequencies. We just don't see it because with our eyeballs, because our brains, we just can't see past that 30 frame limit. We see it in video because video has shutter speed and it can make more frames per second, and so we can start distinguishing it. All modern camera video devices have algorithms in them to take out that flashing luminance signal is what it's called. But like they'll detect that flashiness and they'll remove it from our videos. In the old days when we just had regular, then we were dumping straight analog to tape, we would get that flash all the time. And so there were tricks we had to try to avoid getting it in frame, but it was a pain. So we generate at AC naturally, and a lot of devices like light bulbs don't care. So that's great for making light. And when Thomas Edison was developing the light bulb, or I should say, when he was stealing all the work from the workers that he wasn't paying enough to make the light bulb, not to inject any kind of, moral or personal vendetta in there. He was trying to do that not to invent light bulbs, but so that he could become a monopoly on delivering light into people's houses in New York. Thomas Edison wanted to build a power distribution network that he controlled and that he could charge whatever money he wanted for in order to illuminate people's homes. Yeah, it's what all utilities are trying to. It's what every company tries to do. They try to become the monopoly, right? Because of course, competition is no good. We wouldn't want competition in a free market. Trying not to be too political here, but it's coming out. So Edison was working towards that. Now, Edison, for whatever reason, well, he was an idiot, believed that DC was the way to go. He believed really strongly, to the point where he would do demonstrations of killing animals with AC current to show how deadly it was. Yeah, okay. So in order to maintain dominance and show how AC was so bad, look, you could kill something with AC. He never showed anybody what happens when you do it with DC. It's the same thing, okay? Power is power. So what's that? Yes, electric chairs worked on AC, and that's one of the things Edison says, well, look, we kill prisoners with AC. You wouldn't want that in your home. Yeah. So who was Tesla up against? Or so who was Edison up against? He was up against Tesla, okay? And Tesla was, he was weird. He was very, very strange. Didn't treat people very nice either. But at least kept to himself and really wasn't in it for the money. He was in it for the science. Tesla wanted to do some really interesting things, some of them too interesting. But he never was really, Tesla never wanted to patent his stuff, right? He wanted to develop it and give it away to society so that society could use it, which I think is an altruistic motive. So it's like Edison on one side with DC and Tesla with AC on the other. And why would AC win? This natural time dependence allows the use of a transformer, okay? This is a generator, but generators can be hooked up to turbines. Turbines in the form of, say, flowing water. Tesla opened his lab near Niagara Falls for a reason. You could use steam engines to turn these turbines. And in fact, today we still do that by and large. If a power plant is being run off of coal, oil, or natural gas, or nuclear power, it's basically a big coffee maker, boiling water to turn a turbine, okay? So the exceptions there are hydroelectric, that is using falling water in order to turn the turbine. And then, of course, you have solar, which is quantum mechanics through and through. There's no moving parts there at all. We're just trying to get electrons to get happy in silicon. And then wind turbines, which again use the power of the wind to turn the turbine. So except for solar, which is quantum mechanics, every other form of electrical energy generation requires this motion, this turning over of a loop to generate electricity using Faraday's law of electromagnetic induction. And so with that AC, we can implement transformers. Transformers allow us to swap AC up and down, right? Voltage for current and vice versa. And why is this better than DC for electrical power transmission? It's one thing to make electricity. It's another thing to make it sort of far away from the people and bring it to the people. Why don't people want to be next to power plants? They're noisy. They kick out pollution. Well, okay, let me qualify that. Oil, coal, and natural gas kick out direct pollutants where? Two places. The air and the water, because they have to be cooled. And so there's thermal pollution that takes place. Okay? So you got water and air that are being polluted directly. Okay? And those limits, by the way, which were very tight, are now much looser. The nuclear power plant. How much pollution is it allowed to release? Close to zero. Okay? I'm a big fan of nuclear power. Huge fan of it. Not just because I'm a physicist, but because we have a problem right now. I don't know if you noticed. It's going to be like 96 the beginning of May, right? This week or something like that. Like the temp's going up. The climate is changing. We've changed it. And we need something that can provide electricity 24/7, but produces no carbon and no air pollution. The only thing we have that does that right now is what? Nuclear power. Can solar do it? No, I love solar. I put solar panels on everything. My kids, my house, whatever, right? Okay? Put solar panels on it, right? Because during the day, when we need it kind of the most, we're getting the energy from the sun, right? This is a win, right? I love wind power. Is there any wind in Fresno? No, I mean, sometimes, right? So we're not a great place for wind, but we are a great place for solar. How often does it rain in Fresno? Never, right? So great place for solar. Hydroelectric. We've got it. We got mountains right there, right? Okay? Got a lot of excellent friends that I deeply respect but disagree with because they put up on their farms, build more dams. Don't you think if we had more places to build dams, we'd actually do it? Like, why aren't we not damming up every valley that's up there?
We wouldn't have a drought either.
Yeah, we could fix the drought, right? Just move it, right? Save all the water, all that kind of stuff. We're good. Why don't we build dams up there? Geology. We built dams in all the places that are stable. Okay, I lie. That's being unfair. Okay. You could build one in Yosemite. I will kill you. I will. That's the limit of my pacifism, right there. Okay. You go dam up Yosemite. I'm coming after you. Okay. Because there are some places that need to be preserved because they have outstanding natural beauty or incredible ecosystems or whatever the case may be, right? So there are a few places, I concede, where we could build a dam, but we don't because the price of doing that is so much higher, right? We lose too much when we do that. However, all the other places are taken up, except one. There is a place where we could build dams right now to store water and provide a small amount of electricity. Does anybody know where that is? It's called the Central Valley, where these farmer, good friends of mine, want to build more dams. And I'm like, okay, your farm. Again, that doesn't work for different reasons, right? So, yeah, I mean, we're trying, okay? And yes, there's different policy decisions and disagreements about what to do with the water and all that kind of stuff. But in the end, we have an insatiable need for electricity. So under AC, we generate electricity somehow. This is hydroelectric in this picture, right? Okay, it's by Paul Hewitt of San Francisco Community College. So you generate it, and then you can transform it. So we generate electricity at around, I think it's about 50,000 volts is like a standard generator in a dam and a turbine in a power plant and all that kind of stuff. We generate that power about 50,000 volts, and then we send it places across the state, across the nation at anywhere from 250 to 1 million, 250,000 to 1 million volts. So like you go out to the power lines on the 99 and then like the big ones out towards the 5 over in the West Valley, okay? Those lines were 500,000 volt lines 20 years ago. I think they're 750,000 volt lines, and the 1 million volt lines they're retrofitting. Good friend of mine's a PG&E lineman, right, working on all this stuff. And so he's been giving me the inside scoop. Oh, no, politically, where do you stand? No. Okay. So what are we doing, right? Yeah. Answer this question correctly. Damn Yosemite or not? By the way, we already did. Does anybody know that? What? We damned Yosemite. Does anybody know what it's called? Hetch Hetchy. Go look up Hetch Hetchy. H-E-T-C-H. Hetchy. But yeah, it was another Yosemite Valley just north of Yosemite Valley along the Tuolumne River that got dammed up in 1918, 20, something like that. Basically, it looked like a miniature Yosemite Valley. They put a dam on it. It doesn't look like a miniature Yosemite Valley anymore. So we go from 50,000, say, up to 500,000. Okay, we'll explain why in a second. But when it gets to your house, what does it need to be at? What voltage? 240 when it gets to your house. At your house, they'll split the 240 into two 120s, a 120 plus and a 120 negative. Okay, that happens inside the electrical panel at your house. But when it delivers to your house, it delivers at 240. So how do you get from 50,000 up to 500,000? Step up, transformer, right? Can't be done with DC. Why can't it be done with DC? There's no change in magnetic flux, right? In order for a transformer to work, you have to have a change in magnetic flux. The only way you can have a change in magnetic flux is if your current is changing, right? To make that changing magnetic field. And so AC is a feature, transformers are a feature of AC only. So we're up to 50,000 volts, and we got to get down to 240. So what are you going to do along the way? You're going to start stepping it down, right? So it comes into the city, probably comes in at 50,000 volts again. It gets into different substations where they drop it to about 20,000 volts. That's usually the voltage that's in the line that's maybe next to your house, okay, if you've seen power poles that have the power lines on them, right? And then eventually they'll get it down to 240. So why do all of this, right? What's the advantage? Why not just send 240 volts DC to our houses? There was an equation that I told you about a long time ago, and I called it the power lost equation. And it was I squared R. Okay? This is an equation that tells you, like, how much power resistance is going to use in a circuit. What do resistors or any resistance in the circuit do? They convert the electrical energy into thermal energy, into heat, which is useless. Okay? Unless, of course, you want a heater. Okay? If you want a heater, this works just fine. Okay? And a lot of electric heaters, this is exactly what happens. So there's this resistance wire in there, you run current through it, turns the electricity into heat. But it's called power lost for a reason. The wires that connect us to the power plant are made of not superconductors, meaning that they have resistance to them, right? And there's really nothing we can do about that resistance because resistance is a function of length and cross-sectional area. Well, we can increase the cross-sectional area of a wire, but only to a certain point. If we make it too big, what's the wire going to do? Too heavy, it's going to collapse under its own weight. Okay? What's that? Too expensive. Like there's limitations to how big we can make the wire. But we need to make the wire a certain distance. And remember, resistance increases with length. The longer you make a conductor, the more resistance there's going to be in it. How then do you keep the power being lost to heating up the wires in our transmission circuits? Reduce the current. Between 500,000 and 1 million volts on a line, you can bring the current effectively to zero. Like nanoamps in that wire. And so you go from losing tens of thousands of dollars per kilometer of line, like when you're trying to transmit it like DC, to losing nanocents per kilometer, right? However, you don't want 500,000 volts coming to your house. My son's living in an apartment. He's up in Idaho. We were on a call with him and lightning struck. And I could tell that lightning struck like really close to him. The next day he texted me and said, yeah, it hit the girls' dorm and all the internet and power is out. Right? Like you don't want 500,000 volts at your house because explosions will happen. But if we can trade, we can keep the lost power down, right? Because who's going to get charged for this lost power? The consumer, right? Who's always going to pay for a tariff? Us, right? So, yeah. So that's why AC wins. But DC works really well for computers. So we got to be able to trade back and forth. You'll learn about that in Physics 4C. Next time we come together on Thursday, I'm going to do all of chapter 32. It'll be good. We'll make it. I'll see you then.